thank you for your that you agreed to be on our seminar, and the time is yours.
Okay, thank you very much for this invitation and this opportunity to speak. So, as the title says, this is a talk on some results on the greatest common divisors of terms of linear recurrences. So, let's see a bit the structure of this talk. I will start with an introduction to these problems on GCDs of terms of linear recurrences, some of the important results and what can be done. Then I will focus on a special case, which is that of the greatest common divisor of n and the nth Fibonacci number. In turn, this special case can be divided into two main themes, which are the theme of the fibers, as I call it, and of the image. Then I will talk about a variation of this problem, which is the study of the greatest common divisor of a shifted prime number and the corresponding Fibonacci number. And again, this can be divided into two themes, the one of the fibers and the one of the image. And this is not only a variation of the previous problem, but is also related in some way, which I'll clarify later. By the way, if you at some point have any question, feel free to interrupt me or write in the chat, and I'll try to answer them. All right, so let's start with the introduction to these greatest common divisor problems for linear recurrences. Well, maybe it's better just to be on the same page, a bit of refresh on linear recurrences. I say that a sequence U of integers is a linear recurrence of order k if every term after the first k terms is a fixed linear combination of the previous k terms, as written in equation 1. And the smallest k for which this occurs is said to be the order of the linear recurrence. Also, usually one defines a polynomial for the linear recurrence, which is called the characteristic polynomial. And as you can see, essentially is determined by the coefficients A sub I of the linear combination of equation 1. Also, the first k terms of the linear recurrences are called the initial condition of the linear recurrence. And together, the characteristic polynomial and the initial condition determine completely the linear recurrence, because we know how to start and how to compute every other term. Classic example of linear recurrence is the sequence of Fibonacci numbers, in which the first two terms are 0 and 1, and then every other term is the sum of the preceding two terms. Let's see some other example just to know. Geometric progressions are linear recurrences. Precisely, this geometric progression is a linear recurrence of order 1 and characteristic polynomial x minus the ratio of the geometric progression. Also, sequences of the form a to the n minus 1 for a fixed integer a, it can be proved that they are linear recurrences. I already said this, the sequence of Fibonacci numbers is a linear recurrence of order 2, because we sum the previous two terms. and the characteristic polynomial is x squared minus x minus 1. Then there is a generalization of Fibonacci numbers, which is that of Lucas sequences. And this is also a class of linear recurrences, but I will give more details later. Then we have that every polynomial sequence, Pn, where P is a polynomial, for example, with integer coefficients, is a linear recurrence of order k equal to the degree of the polynomial plus 1. This maybe is not so obvious, but it can be proved. It's not difficult to prove. And the characteristic polynomial in this case is x minus 1 to the k. All right, so these are just some examples of linear recurrences. Now let's move to the theme of greatest common divisors of terms of linear recurrences. Many authors have studied these GCDs, and probably the first important result is this one in the box, which is due to Bugeaud, Corvai, and Zagna, essentially 20 years ago. Let's see what it says. Let A and B be two multiplicative independent integers greater than 1 and fits some small epsilon. Then we have that the GCD of A to the n minus 1 and B to the n minus 1 is less than the exponential of epsilon n for all sufficiently large n. So essentially, what is saying this result? We have two linear recurrences, A to the n minus 1 and B to the n minus 1. Their GCD for sufficiently large n is small because they are somehow related, since the A and B are multiplicative independent, and so there's no reason why the GCD should be big. And so this is the first important result on GCDs of terms of linear recurrency. This result is not effective, meaning that this sufficiently large is not, it cannot be given explicitly because the proof depends on Schmidt subspace theorem, which is an ineffective result. Then after this result, there were given many variation, possible generalization. Here just for instance, I give one due to Fuchs, which says that if U sub n and V sub n are two linear recurrences, so now the setting is more general than A to the n minus 1 and B to the n minus 1. However, we want that these two linear recurrences have characteristic polynomials having only positive real roots. And we also want that U sub n over V sub n is not a linear recurrence. Then there exists an explicit constant C, such that the GCD of U sub n and V sub n is small, meaning it is less than the minimum of U sub n and V sub n to the C for all sufficiently large n. So this is a possible, I would say, variation on
Excuse me, Carlo,
yeah.
Can I have one question? This constancy is dependent on the sequences UN and VN?
Yeah, I would say that because it's dependent probably on the roots of the characteristic polynomials.
Okay, I see.
It is not
Thank
absolute.
you.
Okay, so this is just one of the possible variations. There are many others. And indeed, if one is interested on this topic, I recommend to read this survey of Tron, the greatest common divisor of linear recurrences, which has a collection of results on this theme. What in general is difficult to do is to prove pointwise results. For example, we have this still open conjecture of Ailone-Rudnick, which says that if A and B are multiplicatively independent integers, then there exist infinitely many positive integers n such that the GCD of A to the n minus 1 and B to the n minus 1 is equal to the GCD of A minus 1 and B minus 1. This is the minimum possible value of the GCD of the term of the true linear recurrence. And Ailone-Rudnick conjectured that this equality should be satisfied infinitely many times, and this seems so by doing some experiments. However, a result which is so precise, so pointwise, is still an open conjecture. 19 years old now. All right, so here we come to the main topic, which is the GCD of n and the nth Fibonacci number. As I said, it's difficult to give a pointwise result, and so I try to put myself in the most easy setting, which was not hopefully trivial, which is taking as the first linear recurrence simply the sequence of natural numbers n, which, as I said, is a polynomial sequence, and so a linear recurrence. And then, in order to have something which is not trivial, as a second linear recurrence, I picked the sequence of Fibonacci numbers. So let's start with the GCD of n and Fn and the fibers. So what are these fibers? For each positive integer k, I define the fiber as the set A sub k, which is the set of natural numbers n, such that the GCD of n and Fn is equal to k. Now recall that the natural density of a set of positive integers S is defined as the limit of the ratio of the number of integers in this set which are less than x over x, of course, whenever this limit exists. Then we have to define two functions for each positive integer n. Let Zn denote the so-called rank of appearance of n, which is the smallest positive integer k, such that n divides the kth Fibonacci number. It is well known that this integer exists, and so Zn is well defined. Moreover, let's put Ln to be equal to the least common multiple of n and Zn. The function L is important in this setting because it has this property. We have that every integer m divides the greatest common divisor of n and Fn, if and only if Lm divides n. So we have this important property of L. What can be said on these fibers? Tron and I proved some years ago this result. For every positive integer k, we have that the natural density of the fiber A sub k exists, and is equal to this infinite series involving the Mobius function at the numerator and the function L, which I introduced before. And this series converges and converges absolutely. Also, we have that the natural density of the fiber is positive if and only if the fiber is not the empty set, and if and only if K is equal to the GCD of Lk and F sub Lk. So we have a concrete test, this equality, to check if the natural density is positive or not. Okay, so this is the first result on the fiber. And now I'd like to give a sketch of the proof. I hope to not get too much into technical details, so I'll try to give a hint of the main ideas and tools which are used to do this. So the first idea is to move from the set A sub k to the set B sub k, which is defined in the following way. For each positive integer k, we let B sub k be the set of positive integers n such that k divides the GCD of n and Fn, which is the first condition. The second condition is that if a prime number p divides the GCD of n and F sub n, then p must be a prime factor of k. So it is quite close to A, because for A we have that the GCD of n and F sub n must be equal to k. For B sub k we have that it must be divisible for k and having only prime factors coming from the prime factors of k. Then it is a standard application of the inclusion-exclusion principle, that the number of elements of A sub k which are less than x is equal to this sum involving the counting function of B sub dk with the divisor of k. So at this point, it's sufficient to prove this lemma, which says that for each positive integer k, the natural density of B sub k exists and is equal to this sum, where the series converges absolutely. Why it's sufficient to prove this lemma? Because this lemma, together with equality 2, gives the main result. Indeed, here are the details, but it's just a matter of switching two sums using essentially the fact that these series are absolutely convergent, and so one can do the switch. And so, assuming the previous lemma, one gets the desired formula for the natural density of A sub k. So at this point, one has to prove the lemma. So how can we compute the natural density of B sub k? Let's start by defining this function, tau nd, which is equal to 1 if d divides the nth Fibonacci number, and otherwise is equal to 0. Of course, this is a multiplicative function in the second argument. So we have this equality for relative prime d and e. Moreover, we have that a natural number n belongs to B sub k if and only if Lk divides n, which is equivalent to the first condition. K divides the GCD of n Fn because of the property of L. Also, we need that tau and p is equal to 0 for all prime numbers p which divides n but does not divide k. This is equivalent to the second condition, which said that the prime factor of the GCD of n and F sub n must be all prime factors of k. So this is equivalent because of the definition of tau. At this point, we have a nice way to write the counting function of B sub k. Because of these two conditions, this is equal to the sum over the natural numbers not exceeding x, which are divisible by Lk, and such that the values of tau and p are all equal to 0 for the right primes. So we can use this product to express this property. And then the product can be expanded by using the Mobius function. And again, we have the usual tricks of switching sums. And at the end, without going too much into details, essentially we get what we want, except for the fact that this is not an infinite series, but it's a sum up to x. And we have the float function, but we would like to have as in this lemma, to have nothing, just the ratio of the Mobius function and L dk. So now it's a matter of do a bit of error terms handling. So as a consequence, we can rewrite the counting function of B sub k in this way, where we have the first term is what we want, but we have this error term, Rx, which is defined in this way, involving the fractional part. And so in order to prove that the natural density of Bk is equal to the desired series, we have to show that the other term is a little o of x. All right. And actually, it's sufficient to prove that the series converges absolutely. So one can take two pigeons with one stone. Indeed, if the series converges absolutely, then the error term Rx can be estimated in this way. First, taking the absolute value, then the first square root of x terms of the sum are just bounded trivially by x to 1/2, while the other terms are bounded using the fact that the fractional part of a number less than 1 is the identity function. And then using the absolutely convergence of the series, the last series is the tail of an absolutely convergent series, and so it goes to 0, and we get that the other term is a little of x. So it remains to prove that this series converges absolutely, but I'm not going to talk about the details. The convergence of the series can be proved using properties of L and some bounds of analytic number theory. When we first proved the absolutely convergence, Tron and I proved a lower bound for the function L, since it is at the denominator, so we want it to be big to have convergence. I was saying we proved a lower bound holding for almost all natural numbers, which is fine, but then the reviewer of the paper found a simpler proof of the convergence, and so we went with that proof. I guess that in the first preprint on the archive, there's still the more strong claim on the lower bound of it. So this was a bit of a sketch of the proof of the formula, the existence and the formula for the natural density of the fiber. But if you remember, the theorem also gave a criterion to understand when the natural density is positive or is equal to 0. So it remains to prove that the natural density is positive if and only if the fiber is not empty. In turn, if and only if this equality holds, K is equal to the GCD of Lk and F sub Lk. In fact, the last equivalence is relatively easy, while the difficult part is the first equivalence. Of course, one direction is obvious. If the fiber is empty, then the natural density is equal to 0. The other direction is less obvious. One could be tempted to use the formula. Since now we have a formula, one could try to understand when this series is or is not equal to 0. However, we tried to do this, but we didn't find a way, and so we had to took another route. We used the so-called set of multiplers. So let's see what is the idea. For any set of positive integers S, let n S be the set of all natural numbers which are not multiples of elements of S. So all the natural numbers which are not divisible by any element of S. And we have this lemma, which is due to several people independently. I guess one of them is Erdős, but I could be wrong. Anyway, there's this elementary lemma which says that if S is a set of positive integers for which the sum of the inverses converges, then the set of non-multiplers of S has a natural density. Moreover, this natural density is positive if and only if one does not belong to S. Of course, if one belongs to S, then NS is empty, so the natural density is 0. The other direction is more tricky. And why this lemma is useful for us? Because we have this other lemma, which says this thing. For each positive integer k such that the fiber is non-empty, we have that the fiber is given by the natural numbers of the form Lk times m, where m is not a multiple of any of the elements of this set, big L sub k, which is given by the prime factors of k and then some other numbers depending on L. It is an infinite set. So essentially the fibers are closely related to a set of non-multiplers. Since it can be proved that the sum of the inverses of the elements of big L sub k converges, and that one does not belong to L sub k, then we get that the natural density of A sub k is positive if and only if A sub k is not empty. And so the proof of the theorem is complete. So one has to prove this second lemma, and for the convergence of the series, essentially one uses the convergence of the series, this series. All right, so this is the first result on the fiber. Okay, then there is a generalization to Lucas sequences. So let's just say what are these Lucas sequences. A Lucas sequence is a linear recurrence such that the first two terms are 0 and 1, and then it has order 2. So all the other terms are a linear combination of the previous two terms. A Lucas sequence is said to be non-degenerate if the ratio of the roots of its characteristic polynomial, which has degree 2 and thus 2 roots, is not a root of unity. And so Lucas sequences are a generalization of Fibonacci numbers. And in a natural way, for each Lucas sequence, we can define the set of the, we can define the fiber as the set of the natural numbers n, such that the GCD of n and u sub n is equal to k. And we can also define the rank of appearance, here called as z sub un, as the smallest positive integer k, such that n divides u sub k. Here there's only a little restriction that in order to exist, for the rank of appearance to exist, we need that n is coprime to the coefficient a sub 2. And then similarly to before, we define the function L sub u n as the least common multiple of n and z sub u n. And then we completely analog technique, one can prove that indeed we did the same, this in the same paper. For every positive integer k, the natural density of the fiber a sub u k exists and is equal to this series involving the function L sub u for all non-degenerate Lucas sequences u. And we have a similar criterion for the existence of for the positivity of the natural density of the fibers. Okay, here I forgot of the fiber is positive. So we have the natural density of the fiber is positive if and only if the fiber is not empty, if and only if these conditions. All right, so then other people worked on similar problems. For example, we have that Kim gave a similar result, but instead of Lucas sequences, she considered elliptic divisibility sequences. And then Master Stefano and I studied what happens for a general linear recurrence, well, at least non-degenerate, but this is not a big restriction. And we showed that in general, if u sub n is a non-degenerate linear recurrence, k is a positive integer, then the set of natural numbers n such that the GCD of u sub n and n is equal to k has a natural density, and this natural density is 0 if and only if this set is empty. What is missing here? Well, two things are missing: a formula for the natural density, we did not provide it, and a criterion to establish when the natural density is positive or not. Those are two open problems for us. If I remember well, we did some special cases, but in general, we did not solve them. All right. So now we can move to the theme of the image. So let G be the set of all numbers of the form GCD of n and the n Fibonacci number. For example, we have that 10 belongs to this set since 10 is equal to the GCD of 30 and the 13th Fibonacci number. Equivalently, one can say that G is the set of K such that A sub K is not empty. The first elements of G are these numbers. It is not immediately clear how to establish when a number belongs to G, but we saw before an effective criterion to establish when the fibers are not empty, which is repeated in this lemma. N belongs to G if and only if n is equal to a GCD of Ln and the LNF Fibonacci number. This is a effective criterion that can be tested. All right, so for us, the question was how big is this set G? Doing some numerical experiments, it seems that the counting function of G is asymptotic to x over log x to c, where c is a constant about 0.6. But of course, these are numerical experiments, so it's difficult to say how much they are close to the truth. This is just a graph up to 1 million. It seems that converges to 1, but who knows? And this 0.63 doesn't seem to be related with other constants. Well, after all, just 2 digits. However, we have these results. Leonetti and I proved a lower bound for the counting function. We showed that it is at least of the order of x over log x. And we showed also an upper bound. We showed that it is a little of x. So the set G has natural density 0. And now I'm going to show some of the tools of the proof of this result. First, I recall that the relative density of a set of prime numbers P is defined as this limit, the number of elements of P which are less than x over log s, which is the asymptotic for the prime counting function. Of course, whenever this limit. Then for each positive integer m, I define z sub m as the set of prime numbers P for which the rank of appearance of P is divisible by n. And this, of course, is a set of prime numbers. Okay, the key tool in the proof of the previous bounds for the counting function of G is the following result due to Kubre and Rose, which provides the relative density of the sets Z sub m. It says that for each positive integer m, the relative density of Z sub m exists, and it is given by this expression, where, as you can see, essentially we have a multiplicative function which is given by the product, but there is this correction factor R of m, which is equal to 1 or 5 over 4 or 1/2, depending on the residue class of m mod 20. Okay, so in particular, the relative density of these sets is always positive because this is a positive number. Let us see the sketch of the proof of the upper bound, which is very, very short. We have the following lemma, which I'm not going to prove. If n belongs to G, and LQ divides Ln for some prime P, I'm sorry, Q, then Q must divide N. Now, what is the idea of the proof? First, we fix a small epsilon. We want to show that the naturality of G is less than epsilon. Then we pick a prime Q such that 1 over Q is small. And we, for the sake of notation, we put big Q as Z of LQ. So all the prime numbers P for which the rank of appearance is a multiple of LQ. Then, by Q result, we have that big Q has a positive relative density in the set of prime numbers. And as a consequence, this, let's call it Mertens style product over the elements of q which are less than y, for y sufficiently large, is small, is less than epsilon over 2. Then the idea is to use this lemma. We split G into two subsets. The first is the one of elements without prime factor on big Q, Y. And the other part is the complementary set. If n belongs to G2, then it means that n has at least one prime factor in big Q, Y, which in turn means that LQ divides the rank of appearance of P. But then, consequently, LQ divides Ln, because P divides N, and P divides Zn, and so Ln. Therefore, by the previous lemma, we have that Q divides N. In other words, all the elements of G2 are multiples of Q. So what happens? That the x over x is less than the same ratio for G1, but this can be computed by essentially a simple sieve, and it is given by this product. Plus the same ratio for G2, but we said that the elements of G2 are all multiples of Q, and so this ratio is less than 1 over Q. By construction, these two terms are both small, and therefore we get that the natural density of G is arbitrarily small, and so it must be equal to 0. So this is the proof of the upper bound, at least a brief sketch. All right. So the upper bound was, in fact, improved recently by Ja and I. Showed that not only the counting function of G is a little O of X, but it is less than X log X over log X. This is not a big improvement, but it is still an improvement. And in fact, we proved this more generally for non-degenerate Lucas sequences. How we did that? The trick is that instead of using the result of Kubre and Rose, the one for the relative density of the sets Z sub M, we used a more precise version, which is given in this paper of mine, which not only, first it is a version for essentially general Lucas sequences. There are some mild hypotheses, but essentially for Lucas sequences, not only for Fibonacci numbers. And this result not only gives the relative density of the sets, but it also has an asymptotic formula with an error term. And so one can repeat this previous reasoning, but taking into account all the error terms, and thus getting the more precise upper bound. All right, and this is a result of this paper of mine. In fact, improving that upper bound was the main motivation of working on this formula. So in light of the previous results, we have this lower and upper bound for the counting function of G, but as you can see, they are quite far from each other. So it is still an open question to understand the right order of this counting function. So open problems, what is the true order of this function? Is it true that a formula of the form counting function of G asymptotic to X over log X to the C for some constant C holds. These are some open questions. All right, and now we can move to the second part of the talk, which however is shorter, which regards the GCD of a shifted prime and the corresponding Fibonacci number. So this is a variation. Instead of considering natural numbers, we considered shifted prime. Of course, considering prime would have not made sense because we would have had the GCD of P and FP, which is usually 1, so not interesting. But for shifted prime, I hope it's a bit more interesting. By the way, shifted primes already appear in relation to Fibonacci numbers. For example, it is well known that P divides Fp minus 1 for every prime number which is equal to plus or minus 1 mod 5. So in this setting, for every positive integer k, we define the set P sub k as the set of prime numbers P for which the GCD of P minus 1 and F sub P minus 1 is equal to k. So these are the fibers in this setting. And Jia and I proved an analog of the result of Tron and I. We showed that for each positive integer k, the relative density of the fiber P sub k exists, and it is given by this infinite series, which is very similar to the previous one, but now at the denominator we have the Euler function phi. And this series converges absolutely. Moreover, we also have an effective criterion to establish when the relative density is positive. Here the criterion is a bit more complicated because essentially it can happen that the fiber consists only of the prime number 2. So there's only this technical complication. Now, the proof of this formula, without much surprise, proceeds in a very similar way to the formula for the fibers A sub k, but it requires a result from the distribution of prime numbers in arithmetic progression. However, the proof of the claim on the positivity of the relative density is different, because it requires the following theorem that Leonetti and I proved previously, but for unrelated reasons. This plays a role similar to the theorem with known multiples, which was used in the other proof. So let's see what it says. Given some natural numbers, m sub 1, m sub 2, blah, 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 m sub k, let BQ be the set of prime numbers P, such that each of these P is not equal to 1 modulo any of the sub I integers. Then this set Q has a relative density in the set of prime numbers. And we have this lower bound for the relative density. And this lower bound says that the relative density is positive, I would say, except when one of these integers, m sub I, is equal to 1 or 2. So the trivial cases. Okay, so using this result, we can prove in a similar way to the one of before, this result for the relative densities of the fibers. All right, so what about the image in this setting? Let's define K to be the set of all integers of the form GCD of P minus 1 and F sub P minus 1 for some prime number P. I assumed P greater than 2, but there's no restriction on that. Equivalently, we can say that big K is the set of natural numbers K such that the relative density of P sub K is greater than 0. And one can notice that big K is a subset of G because we are, for G, we consider it all natural numbers, then now we are considering only numbers of which are shifted primes. So big K is a subset of big G. Therefore, from the upper bound of the counting function of G, we get immediately an upper bound for the counting function of K. What about a lower bound? Jai and I show with this lower bound. The counting function of big K is at least of the order of x over log x. And what perhaps is interesting is that we proved this lower bound by elementary methods only. Especially, we did not use the Kubler-Ross result or my generalization of it, which are based on the Sebotare density theorem. So this lower bound can be proved with elementary method without Sebotare theorem. And since, as I mentioned before, K is a subset of G, from the lower bound we also get K, we also get the lower bound of G. So essentially we found an alternative proof which uses only elementary method for the lower bound of G. This might suggest that with some clever techniques which are only elementary, one can maybe improve all the bounds and also find the correct order of the function G. But this is just a guess. Of course, the open problem is what is the true order of K? And we do not have a conjecture, but probably if somebody tried to plot a graph similar to, where is it? To this one, can come up with some conjecture. Anyway, what is the order is an open problem. Then one can surely do some variations. For example, instead of considering only shifted primes P minus 1, one could consider the GCD of P plus 1 and F of P plus 1, and also the other possibilities of the signs. I have to say already for P plus 1 there are some technical difficulties because one has to find a similar theorem with minus 1 here, and that's a bit tricky. So it could be not obvious. And of course, one can try to extend the previous results to look at sequences or even more general sequences. All right, so that's all from me. Thank you very much for your attention.
Thank you very much, Carlo.